Lieutenant Colonel Arthur Langley removes his spectacles and leans closer to the workbench. It's 14th September 1943, inside the Ordnance Examination Facility at Chobham, Surrey. Before him sits a Bosch turret traverse motor, serial number TT477B, extracted 3 days earlier from a Tiger I destroyed near Salerno. The motor housing is intact. No bullet impacts, no shrapnel damage. The external casing shows standard factory finish, dark grey enamel over machined steel. But the motor itself is silent, dead. The Tiger's crew had abandoned the tank not because of armor penetration or track damage, but because they could no longer traverse their main gun. Langley's team has examined 17 Tiger components since July. 11 showed similar electrical failures. That's a 64.7% failure rate in a system designed to rotate a turret weighing 11,000 kilograms with such precision that gunners could track moving targets at 2,000 meters. The German propaganda films showed Tigers dominating battlefields, their 88mm guns swiveling smoothly to engage multiple targets. The reality sitting on Langley's bench tells a different story. The motor weighs 23 kilograms. Langley's assistant, Technical Sergeant Dennis Whitmore, has already removed the 6 securing bolts, each 12mm diameter, torqued to factory specification of 85 Newton meters. The casing separates cleanly. Inside, the armature remains fixed to its shaft. The commutator segments show even wear patterns. The brush assemblies sit in their holders with 8mm of carbon remaining, well above the 3mm replacement threshold. Langley rotates the shaft manually. It turns freely through 360 degrees. No bearing roughness, no shaft wobble exceeding 0.1mm. He connects a test battery. 24 volts direct current, standard Wehrmacht specification. The ammeter needle doesn't move. Zero current flow. Not a short circuit, an open circuit. Somewhere in this motor, the electrical path has broken completely. Whitmore strips the armature from its housing. The commutator comes away easily once the retaining ring is removed. Each copper segment is soldered to its corresponding armature winding. Langley examines the joints under magnification. German manufacturing standards specify 60 to 40 tin lead solder applied at 240 degrees Celsius minimum. Proper solder joints appear smooth and slightly concave, where surface tension drew the molten metal into the joint. These joints look correct. Shiny copper-colored surfaces. No visible gaps. No cold solder appearance. That dull, grainy texture indicating insufficient heat during application. He probes one joint with a steel pick. The solder flexes slightly, but holds. He probes another. Same result. The third joint separates under minimal pressure. The solder simply lifts away from the copper segment, leaving the wire end exposed. No force required. Just the gentle pressure of a blunt tool. Langley tests every joint systematically. 19 of 32 show the same failure. The solder hasn't cracked from vibration or thermal cycling. It has never properly adhered to the copper in the first place. He places a sample under the facility's metallurgical microscope at 100 times magnification. The copper surface shows a dark film between metal and solder. Copper oxide. When copper oxidizes, solder cannot wet the surface. The molecular bond never forms. Proper manufacturing procedure requires flux, typically rosin-based, to remove oxidation and prevent reoxidation during soldering. Langley sees no evidence of flux residue. The dark oxide layer is uniform and undisturbed. Someone assembled this motor without proper flux application, or using flux so degraded it provided no cleaning action whatsoever. The implications extend beyond this single motor. Langley reviews the examination records for the 10 previous motor failures. 7 show identical soldering defects. 1 failed due to brush spring failure. The spring steel measured 180 Vickers hardness, when specification requires 400 minimum. Two others exhibited insulation breakdown in the field windings, the varnish coating cracked and contaminated with metallic particles. None of these failures resulted from combat damage or operational abuse. The Tigers were being destroyed by manufacturing defects that should never have passed factory inspection. Each motor would have undergone acceptance testing before installation. Each should have been energized on a test stand and operated under load. Yet motors with 60% of their solar joints compromised were installed in tanks and shipped to the front. The Bosch factory in Stuttgart produced these motors at a rate of approximately 180 units per month throughout 1942 and early 1943. Tiger production reached 56 units per month at peak. Each tank required one traverse motor and one elevation motor of similar design. That's 112 motors monthly for new production, plus spares for field maintenance. The production schedule allowed 3.7 hours per motor, including winding fabrication, assembly, testing, and crating. In peacetime, Bosch engineers estimated optimal production time at 8.5 hours per unit to maintain quality standards. The time compression is brutal, 56% less time to complete identical work. Something in the process had to give. Langley examines the motor's data plate. Manufactured February 1943. Inspector stamp, K47. The stamp indicates which quality inspector approved the motor for service. Wehrmacht production facilities employed hundreds of inspectors, each assigned a unique identifier. K47 appears on 5 of the failed motors in Langley's collection. He requests production records through intelligence channels. The response arrives 12 days later. Inspector K47 was Karl Hoffmann, a 52-year-old former toolmaker conscripted into inspection duty in December 1942. Hoffmann's inspection rate averaged 47 motors per 8-hour shift in February 1943. That's one motor every 10.2 minutes. The inspection protocol specifies 40 minutes per motor. Visual examination of all solder joints, insulation resistance testing, operational testing under no load and loaded conditions, vibration testing, and documentation. Hoffmann was inspecting motors at 1/4 the time required to perform the specified tests. He wasn't incompetent, he was drowning. The Tiger's hydraulic turret traverse system could rotate the turret through 360 degrees in approximately 1 minute when functioning properly. The electric motor drove a hydraulic pump producing pressure of 150 bar, roughly 2,175 pounds per square inch. That hydraulic pressure acted on a motor connected through reduction gearing to the turret ring. The system gave the gunner 2 modes: powered traverse for rapid target engagement and manual traverse using a hand wheel for fine adjustments. In combat, powered traverse meant the difference between getting the first shot and receiving it. British testing of captured Tigers showed turret traverse time averaging 58 seconds under powered operation. Sherman tanks of the same period required approximately 15 seconds for powered 360-degree traverse. The German system was already slower. When the traverse motor failed, German crews reverted to manual operation. The gear ratio necessary to allow human power to rotate 11 tons of turret meant each revolution of the handwheel produced 0.72 degrees of turret movement. A 90-degree traverse required 125 complete revolutions. Sustained turning effort of approximately 15 kilograms force. Under combat conditions, with adrenaline and desperation, a fit crew member could manage perhaps 30 revolutions per minute. That's 4.2 minutes to rotate the turret 90 degrees. An eternity. Near Villers-Bocage on 13th June 1944, British forces encountered Tigers from the 101st SS Heavy Panzer Battalion. After-action reports describe one Tiger, designated number 222, maneuvering to engage a column of Cromwell tanks. The Tiger fired, destroying the lead Cromwell at 800 meters. The commander ordered turret traverse to engage the second Cromwell, now accelerating to flank the Tiger. The turret didn't move. The gunner reported traverse motor failure. The crew shifted to manual operation, but the Cromwell covered 200 meters, whilst the Tiger's turret crawled through 30 degrees. The Cromwell's 75mm gun couldn't penetrate the Tiger's frontal armor, but it could penetrate the side armor at close range. The Tiger commander ordered the driver to pivot the entire tank, turning on one track to bring the gun to bear. But sloped terrain and soft ground prevented rapid pivot. The Cromwell reached the Tiger's flank. 3 rounds at 150 meters, 2 penetrations. The Tiger burned, 5 crew killed. Not by superior Allied firepower or tactical brilliance, by a motor assembled without proper flux. The 504th Heavy Panzer Battalion reported 12 Tiger Thwon tanks operational in January 1944. By March, operational status dropped to 7 tanks, despite receiving no combat losses. 5 tanks were deadlined for electrical system failures. Battalion maintenance records list turret traverse motor replacement on 3 occasions, elevation motor replacement twice. The battalion's senior mechanic, Oberfeldwebel Hans Krieger, noted in his maintenance log that replacement motors often failed within 50 operational hours. Standard Wehrmacht reliability targets specified 500 hours mean time between failures for electrical motors in combat vehicles. The Tiger motors were failing at 1/10 the design target. Krieger's log includes an entry dated 8 March 1944. Requested investigation of motor supplier quality. No response received. Langley traces the failure pattern through captured German maintenance documentation. Soviet forces advancing through Poland in early 1945 captured extensive Wehrmacht logistics records, among them monthly failure reports from Tiger battalions. The data shows traverse motor failures increasing steadily from mid-1942 through late 1943. June 1942, 3% monthly failure rate. December 1942, 11% monthly failure rate. June 1943, 19% monthly failure rate. The curve isn't random variation. It's systematic degradation. As production pressure increased, quality declined proportionally. The Germans were aware. A memorandum dated 15 August 1943 from the Heereswaffenamt, Army Weapons Agency, acknowledges recurring reliability concerns with electrical traverse systems and orders Bosch to implement immediate corrective measures. The memorandum specifies that production quotas remain unchanged. Improve quality, but don't reduce output. Mutually exclusive imperatives. The Bosch Stuttgart facility employed approximately 1,400 workers in early 1943. Of these, roughly 600 were foreign conscript laborers, primarily French and Polish workers, transferred from occupied territories. The soldering operations employed mainly female workers, both German and foreign. Training for soldering positions lasted 3 days in 1942. By mid-1943, training was reduced to 1 day due to labor shortages. The soldering stations used rosin flux supplied in paste form, applied manually with small brushes. Proper technique required cleaning the copper surface with fine abrasive cloth, applying flux liberally, heating the joint with a 180-watt soldering iron until flux began to smoke, then applying solder wire until the joint filled completely. Each step mattered. Skip the cleaning, and oxidation prevents bonding. Insufficient flux, and oxidation forms during heating. Inadequate heat, and the solder doesn't flow properly. Excessive heat, and the flux burns away before solder application. The process required judgment and experience. A worker producing adequate joints in peacetime might complete 8 per hour. Production quotas in 1943 demanded 15 per hour. The only way to meet quota was to accelerate each step. Minimal surface preparation, thin flux application, rapid heating, quick solder application, move to next joint. The solder looked acceptable. Shiny surface. Apparently complete fill. But the molecular bond never formed properly. The motor would pass visual inspection. It would pass initial electrical testing. The joints had enough contact area to conduct current under no-load conditions. Only under sustained vibration and thermal cycling would the defective joints fail. That failure would occur 100 or 200 hours after manufacture, in a tank somewhere in Russia or Italy or France. Far from the factory. Far from accountability. Langley interviews a former Bosch worker through intelligence channels in late 1944. Margot Schiller, 34, worked soldering armature assemblies from January 1943 until August 1944, when she was transferred to another facility. She describes production conditions. We had quotas. Every day the supervisor posted the numbers, how many assemblies each worker completed. If you fell below quota 3 days in a row, you were transferred to general labor. That meant loading and unloading lorries, cleaning, heavy work. Everyone feared transfer. So we worked fast. The flux containers were often nearly empty. We were supposed to request refills, but that meant stopping work, losing time, falling behind. So we used what remained, sometimes just traces, sometimes dry brushes. The joints looked acceptable. That's what mattered. Appearance. The human cost extended beyond German tank crews. Forced laborers worked alongside German civilians in the Bosch facility. Several former French workers interviewed after liberation described deliberate sabotage, using minimal flux intentionally, knowing it would cause eventual failure. One worker, Pierre Duchamp, stated, "We couldn't refuse to work. We couldn't escape. But we could work poorly. A soldering joint that fails, that's a small victory, a small act of resistance." The distinction between sabotage and survival becomes impossible to pass. Workers under quotas rushing to avoid punishment. Workers deliberately compromising quality to resist their captors. Workers too exhausted and malnourished to maintain precision. All produced the same result: defective motors killing German crews and sometimes failing at moments when that failure might allow Allied soldiers to survive. Langley's colleague, Major Thomas Pemberton, examined the broader patterns in German manufacturing quality during late 1943 and 1944. His analysis of captured equipment across categories, vehicles, weapons, ammunition, optical instruments, showed consistent decline in manufacturing precision. Tolerances widened, materials substituted, processes abbreviated. A Mauser rifle produced in 1940 showed machining accuracy within 0.02 millimeters on critical dimensions. The same rifle produced in 1944 showed accuracy within 0.15 millimeters, 7 times looser tolerance. The rifle still functioned, but accuracy and reliability declined measurably. The same pattern appeared everywhere. Quality as a system-level casualty of total war. The Tigerwaffe, despite its formidable armor and firepower, suffered from a fundamental tension. It was designed as a precision instrument requiring peacetime manufacturing standards, but produced under wartime pressures that made precision impossible. Only 1,347 Tigerwaffe tanks were manufactured between August 1942 and August 1944. Compare that to 49,234 Sherman tanks produced by American factories in roughly the same period. The Sherman wasn't superior in armor or firepower. It was superior in reliability and availability. A Sherman's turret traverse motor, manufactured by General Motors or Chrysler, underwent 90 minutes of inspection per unit, including automated testing that verified electrical characteristics under simulated operational loads. Defective motors were identified before installation. The motor failure rate in Sherman tanks averaged less than 2% over the vehicle's service life. Post-war examination of captured German manufacturing facilities revealed the scope of quality degradation. British investigators examining the Bosch Stuttgart plant in May 1945 found inspection records for motors produced in March 1945. Batch acceptance rate 67%. That means 1/3 of motors produced failed even the abbreviated inspection protocol in place at that time. Production continued anyway. Failed motors were marked for rework, but rework capacity was overwhelmed. Motors were shipped to assembly plants with failure tags still attached. Desperation overrode procedure completely. The lessons reached beyond immediate military application. Post-war manufacturing standards in Britain and America incorporated explicit provisions addressing the patterns observed in German production collapse. The British Standards Institution published revised quality control specifications in 1947 that mandated statistical sampling protocols preventing inspectors from being overwhelmed by volume. If production rate exceeded inspection capacity, production stopped, not inspection. The specification explicitly cited examination of German manufacturing failures 1943-45 as justification. American military procurement regulations adopted similar provisions. The collapse of German quality control became a case study in engineering schools, business programs, and military academies. Not as a celebration of Allied victory, but as a warning about system-level failure modes. Modern museums preserve examples of the equipment Langley examined. The Bovington Tank Museum houses a Tiger I, registration number 131, captured in Tunisia in April 1943. The tank's turret traverse motor has been removed and sectioned for display. Visitors can see the armature, the commutator segments, and, under magnification, the solder joints. Museum documentation notes that this particular motor showed incipient failure, 8 joints with partial separation. The tank was captured before the failure progressed to complete loss of function. The display includes Langley's original examination report, handwritten notes detailing the same defects he documented in September 1943. The physical evidence and the analysis remain connected across 80 years. Langley continued his ordnance examination work through the remainder of the war. He examined captured German equipment ranging from Panzerfaust anti-tank weapons to V-2 rocket components. His reports established baseline understanding of German manufacturing capacity and constraints, information that informed Allied intelligence assessments of German war production sustainability. In November 1944, Langley authored a comprehensive analysis titled Systematic Degradation of German Electrical Component Reliability, Causes and Implications. The report compiled data from 147 examined components, documenting the progression from peacetime quality to wartime failure. His conclusion proved prescient. German manufacturing capacity is self-limiting. Quality degradation reduces operational effectiveness faster than raw production can compensate. The enemy faces industrial collapse regardless of raw material availability or factory capacity. After the war, Langley joined the faculty at Imperial College London, teaching manufacturing engineering and quality control. He supervised doctoral research on statistical process control and reliability engineering. His students included several who would later establish quality control systems at British Leyland, Rolls-Royce, and British Aerospace. He published 17 academic papers between 1946 and 1967, many drawing on patterns observed during wartime examination work. One paper, Human Factors in Manufacturing Quality Degradation, published in 1952, analyzed the intersection of workforce conditions, production pressure, and output quality. It cited the Bosch motor failures as a primary case study. The paper influenced British factory management practices throughout the 1950s, contributing to improved worker training programs and more realistic production scheduling. Langley retired from Imperial College in 1968. He continued occasional consulting work for the Ministry of Defence, examining reliability issues in modern weapons systems. In a 1971 interview for an oral history project, he reflected on the Tiger motor examination. We celebrated finding German equipment failures. Each failure was intelligence, evidence of their declining capacity. But I remember thinking, whilst examining those solder joints, about the human beings who made them. Were they saboteurs? Were they exhausted workers pushed beyond endurance? Were they simply inadequately trained? Perhaps all three simultaneously. The failure wasn't in the solder. The failure was in demanding the impossible and then being surprised when human beings, under impossible pressure, produced impossible-to-sustain results. We won in part because we maintained systems that didn't demand the impossible. Our factories had adequate inspection capacity. Our workers had adequate training time. Our production quotas aligned with human capability. That alignment was as much a weapon as any tank or aircraft. Langley died in December 1979 at the age of 74. His papers were donated to the Imperial War Museum, where they remain available to researchers. Among them, the original examination report for Bosch Motor T477B, complete with photographs of the defective solder joints, metallurgical analysis results, and Langley's handwritten notes. The report concludes with a single underlined sentence: "Quality cannot be inspected into a product. It must be built into the process." That principle, extracted from examining a failed motor in September 1943, became foundational to post-war manufacturing philosophy. Modern quality management systems, Six Sigma Total Quality Management, ISO 9001, all embody that same understanding. The legacy of Langley's work isn't measured in German tanks destroyed. It's measured in manufacturing systems redesigned to prevent quality collapse, in processes structured to sustain human capability rather than exceed it, in products that work because the systems producing them are themselves designed to work. The defective motor sits in an archive box. The lesson it taught shapes manufacturing systems worldwide, preventing failures that will never occur because the understanding gained from past failures created systems that make them impossible.